Let me share my screen and see if I can get this right. Okay. Do you see the full screen?
Yeah.
Okay, good. I hope my internet connection stays stable, but if at any point you lose me, just make sure you let me know and I'll stop talking. And maybe just while the number of participants are increasing and people are coming into the talk, I'll just say a little bit about myself. So yes, Mark already did a very good job introducing what I do, my university, but my research is mostly focused on quantum machine learning. And while that may sound very specialized, I actually think it's become quite a broad field right now. And what I wanted to talk to you about today in particular is like quite a controversial topic or question. But are quantum neural networks actually relevant? And to be honest, before I started my PhD, I would have actually probably answered no, right? And not at least for a very long time. But what I hope to show or discuss with you today is actually there is incremental progress and exciting information or exciting research that's coming out that's actually suggesting that quantum neural networks or parameterized quantum models are in fact different and interesting for a few reasons, which I hope to highlight to you today. So I really love questions and keeping things interactive, and I like using Zoom because I can actually see the questions as they come up. So if at any point anybody has anything on their mind or they want to discuss something, then please just feel free to pop it in the Q&A and we can talk about it. Okay, so I will begin then, right? So okay, forgive me for starting from the basics, but I think it's always very nice to set some motivation for the discussion, the project that we were thinking about, and the whole reason for these results that I will show you today. So machine learning, classically or on quantum, always starts more or less with the same framework, right? Where you have some model, let's say F, and it takes in some data and depends on some parameters. And as a machine learning engineer, you really have two major design choices with your machine learning model, right? So you can choose how to parameterize the model, or you can choose how to pick the model family, right? So this is the two main things that one has to decide on. And of course, the goal of all machine learning is to find some optimal theta, some optimal parameters for your model such that this model gives you some robust predictions or gives you something interesting for a machine learning task. And of course, as a quantum researcher in this field, the whole point or the whole goal is to try and find some integration with quantum such that this becomes even more interesting or perhaps even more robust or more expressive, or maybe these models are more powerful in some sense. And so asking these questions really led to the research project that I worked on for the last couple of months. And by the way, when I speak about models in this talk, then I will mostly be referring to neural networks. And this piece of work that I speak about, oh gosh, okay, there we go, it's changing now. I put the reference to the archive link here, so if you guys want to follow along at home, most of the stuff that I will speak about comes from this paper. And I was very lucky to work with some very talented colleagues from IBM, so David, Krista, Stefan, and then also some people from ETH, Aurelian and Alessio. And we wanted to investigate exactly this question, right? The power of quantum neural networks. So can we in some way get something more interesting from quantum neural networks as opposed to the classical neural networks that we have? And so the first question, of course, is how do we even measure the power of a model, right? Classically or quantumly, if I can say this is even a word. And so luckily in classical literature, there are many ways suggested to do this. So the most naive way is perhaps this one, where you would just simply count the number of parameters in your model, right? So by simply blindly throwing more parameters into your model, then intuitively your model should be able to capture more intricate relationships between data and your variables and so on. But obviously this is not a very elegant way, not a very smart way to do things, because by adding more and more parameters into your model, then you might be adding redundancy into your model, right? Not all the parameters may necessarily be useful in this setting. So you're not actually capturing a good measure of power in your statistical model and your machine learning model. But then there is also the VC dimension, which is super popular in classical neural network literature. And the VC dimension, I mean, the technical details are not so important, but some things I do want to mention about the VC dimension is that, so firstly, it's suggested to be a measure of how expressive a certain class of functions or models are. But there are a lot of problems that go along with it. So in theory, it's a very good measure, but actually computing it in practice is quite difficult. And I say here that these bounds are loose. What I speak about here is something called generalization bounds, which I'll introduce in a few slides. And typically you want these bounds to be quite tight. So this is actually not a desirable property from a theoretical point of view as well. So although the VC dimension is probably the most well-known in neural network literature, it is accompanied usually by a lot of problems. So then there is also now this idea of the effective dimension. And the effective dimension has been around for forever, right? So it comes up in computational complexity theory all the time and a whole lot of other places. But in neural networks and in understanding the power or the expressivity of statistical models, I think this is relatively, I'd say, unpopular. But I don't know why, because I think it's actually quite a beautiful measure with a lot of intuition behind it. So I like this analogy of clouds in the sky, where clouds are embedded in a three-dimensional space, but the space that they actually occupy, their effective dimension, is only 1.37. And so the effective dimension really tries to capture the size of your machine learning model in a high dimensional space. So it actually tries to capture what is relevant, what is being used in your model, as opposed to, for example, simply counting the number of parameters in your model. Okay, so going back to this picture that I introduced in the start, where you've got like some model that belongs to, let's say, a neural network, there are really two mathematical spaces that I want to highlight here. And this is important for understanding the effective dimension, and the effective dimension I'm going to motivate as a useful measure to quantify the power of models. So the first space is this idea of your parameter space. So the parameter space, quite easy to understand, quite straightforward. It's just the space at which you draw your parameters from for your model. But then there is this concept of model space. And model space is really the thing that we are interested in understanding. We're interested in understanding how this thing looks, right? So this is the space of all your model functions for a particular parameterization. So this is probably not a very good picture, but you can think of like each point in model space actually as a distribution. And this distribution belongs to a model with a particular parameterization. And for the longest time, the classical machine learning community studied this space, the parameter space, because they thought that, like, increasing your parameter space, making this infinitely large, will give you access to more powerful models. And this is totally not right? Because and people couldn't understand why uniform, like small little shifts in your parameter space corresponded to massive changes in your model. And this is because uniform shifts in your parameter space don't correspond to uniform shifts in your model space, right? So your model could drastically change even if you make a small shift in your parameter space. And so it took a long time for the community to realize that this is actually the space that is interesting, that we need to understand. And so then the next question, of course, is like, how do we actually traverse from one space to another, right? How do we actually understand the interaction or the relationship between these two mathematical spaces? And the answer to that is a quantity called the Fisher information, which I'm sure a lot of you are familiar with. So I put the equation here for those who are interested, but it's not so important. What is important is that the Fisher information actually gives us a notion of distance in model space. And the square root of the determinant of the Fisher gives us actually the volume in model space. So it gives us an idea of size in model space, which is really convenient. So the effective dimension, I put this like magnifying glass here, is actually something that tries to look into this model space and quantify the size of your model here. So this is the intuition behind the effective dimension. And for completeness, I want to also just put the equation. I think this is probably like the heaviest slide I have, and thereafter it's mostly pictures and results. But I think this equation, although it looks very messy, is actually beautifully simple and intuitive. So what this is saying here is like the effective dimension, we call this D. and it depends on some parameters, gamma and n. So gamma is some hyperparameter which we fix, so you can ignore this for now. And n is the number of data samples that you have available to you when you're modeling, right? When you're doing some machine learning task. So the effective dimension of some model over a full parameter space, capital theta, is defined as this thing here. And if you look at the numerator, you can see we've got a square root of the determinant, and in here is the Fisher information. So in some sense, we've got the volume of a model in model space here, and we average over the full parameter space. So we kind of take the average of all models, their volume in the parameters in the model space, and we normalize by the volume in the parameter space. And what's really cool about the way this effective dimension formula was introduced, so I must also highlight that it was introduced at first in this paper here. But what's nice is that they introduce a scale-dependent version of the effective dimension, meaning that this measure really depends also on the number of data samples you have. So for example, the VC dimension actually assumes that data is infinite, that you have access to infinite data, whereas the effective dimension is really a scale-dependent measure, and the number of data samples that you have actually determines the resolution or the scale at which you peer into model space. So the more data you have, the more clearly you can observe model space. And this is actually quite nice and quite a cool thing. It's like a control parameter that allows you to peek into model space more clearly with more resolution. Okay, cool. So that is the effective dimension and the intuition. And when we came across this measure, we thought, wow, this is really interesting. Like we should definitely use it to understand quantum neural networks or quantum models, and perhaps compare it to classical models as well, classical neural networks. But the first thing we realized was that if we come out with some work that using the effective dimension, then a lot of people are going to say, well, why didn't you use more established measures? And so we really had to motivate more formally why the effective dimension. And so how people normally do that in classical machine learning literature is they usually find a measure of power or expressivity that they think is interesting, and they motivate it in the context of generalization. So what generalization means in machine learning is it tries to understand how well your model will perform on new data. So how will it actually do on brand new samples that it has never seen before? So if it makes mistakes here, or the error that it makes on the new information, on the new data, is called the generalization error. And so what people try to make statements theoretically about is this generalization error, and how this is typically done is through something called a generalization bound. And how this generalization bound looks is you can imagine that you pick some model, and your model will have some inherent true error associated with it. And then you can approximate your model's error with some data. So we call this like this empirical error that you approximate with. And so the difference between the true error in your model and the empirical error that you approximate with data is called the generalization gap, the generalization error. And so usually we try to bound this thing for a particular model. And how it's bounded is with a capacity measure, so a measure of expressibility, a measure of power. And this is exactly what the effective dimension is, right? So it's something that tries to quantify the size of our model in model space and also depends on some data. So this was the first exciting result I think that we came up with in our paper was that we were actually able to bound the generalization error using the effective dimension. So for those of you who are interested in the technical details, then we can talk about it after, or you can read the paper. But what I just wanted to show you was that we were able to actually bound this quantity using the effective dimension, which comes in here. And then just to further verify that the effective dimension can actually capture this generalization behavior, we did a little experiment numerically. And I think it's actually quite a cool one. So it was first introduced in this paper over here. And now I think it's actually become a little bit standard practice to check your new measure that you propose. And in this graph, what you're looking at here is the effective dimension on the y-axis. And what we did was we took a neural network with a fixed architecture, and we had a data set. And we trained this neural network on the data set, on the true data set, with some labels to 0 error. And then we calculated the effective dimension and plotted it here. And then what we started to do was then we started to slowly randomize the labels in the data set. So we started to mix up the true labels in the data. So for example, as we move on the x-axis here, we start to randomize the labels more and more. So for example, this point here is 10% of the labels are randomized. And then we train the same neural network with the same architecture to zero error again, and then calculated the effective dimension and plotted it on this axis. And so what you should see is you should see the effective dimension increasing as you randomize more and more. Why? Because you are introducing noise into your model, right? So you're introducing, you're randomizing your data set. And so it's more and more difficult for the neural network to fit this noise. And so it needs more and more capacity, it needs more and more power to fit this noise that you're inducing artificially into your data set. And so this was very nice for us to see that the effective dimension can actually capture this kind of behavior. Okay, so just a recap, what I hopefully have managed to convince you of is that the effective dimension is interesting. It's a robust measure of capacity or power. Why? Because we show that it actually can bound generalization, and we have this like cool supporting numerics as well. Okay, so then the next step, of course, after we have this measure of power, the effective dimension, is to use it, right? To actually go ahead and calculate the effective dimension of models and see how does quantum fare. So what we chose to look at on the classical side is neural networks that are fully connected, feed-forward neural networks. And while we wanted to keep the study quite broad, we also needed to do something quite systematic. So we limited the models in which we compare. So I'll explain what I mean by that in the next slide. So yeah, so on the classical side, these feed-forward neural networks are really like, I think, part of the building blocks of deep learning. And on the quantum side, what we looked at were these parameterized quantum circuits of a particular form. So this might be an abuse of terminology, but when I say quantum neural network, all I really mean is parameterized quantum circuits, right? So a quantum variational classifier. So some circuit here that depends on some parameters which we train and optimize. And we call two models in either regime comparable if they share the same input size, the same output size, and the same number of trainable parameters in each setting. So classically, we looked at neural networks with and without bias. And on the quantum side of things, we actually looked at a very specific parameterized quantum model. And how it looks like is it has this feature map borrowed from this paper here. So the feature map encodes the data. And then the variational part, the model that depends on some parameters, is quite a straightforward, I think, rather canonical variational form that consists of entangling gates and parameterized RY rotations. And then we did some post-processing. So what we did was we measured every qubit in the sigma Z basis, and then we did something called parity post-processing. So we checked the parity of the output bit strings and then mapped these corresponding probabilities to certain labels. So in both cases, we looked only in all the experiments at binary classification or binary labels, but really all the analysis can be extended to multi-class classification as well. So these are like the two frameworks that we investigated on either side. And then when we looked at the effective dimension of these two models, what we saw was, so now you're seeing the effective dimension here, it's normalized, so meaning that it can be maximum at 1. And on the x-axis is the number of data that you have available. And the quantum neural network just had significantly higher effective dimension, significantly higher power or expressibility. And this was for a fixed input size and output size, and number of trainable parameters in the models are 40. But this trend really persists as we scaled up the models as well. So this was really something that stuck around no matter what we looked at. And something else I want to also just highlight is that this classical neural network that we choose to show here is actually the best one that we brute force search over all kinds of architectures and pick the best classical neural network to plot here. So we looked at, so with these constraints, we looked at all possible configurations one can have. So you can have, like, for example, more than one hidden layer and more neurons in some layers than others and so on. So we really look over all configurations. We search over all possible popular activation functions. So we explored all of these as well, with and without bias. And this is the best one that we find. So this, I think, is quite interesting. Okay, but then the most natural question is why, right? So why does this quantum model seem to be more powerful, more expressive than a very large class of classical neural networks and a very important class of classical neural networks? So if we go back to the effective dimension, the formula, and if you look a little bit closely at it, right? So what do we have here? It's really mostly a function that depends on the Fisher information, really. So I think this is the most important quantity in here. So we then decided to look a little bit closely at the Fisher information and isolate it for the classical models and the quantum models. So what we did then was we looked at the spectra of the Fisher information matrix, right? So we calculated the Fisher information matrix with different parameterizations. So we sampled different parameter sets in each model. So we sampled 100 parameter sets. We calculated the Fisher information 100 times for each model. And then we plot the distribution, the average distribution of the eigenvalues of the Fisher information. So what you're looking at here is the distribution of eigenvalues as a histogram. And what we then immediately saw was that the distribution of the eigenvalues in the quantum neural networks was totally different, right? It was like more evenly spread out, and there were no extreme values. Whereas on the classical neural network, there were these large eigenvalues, and most of them were actually around zero. So these sub figures here is basically the first bin pulled out and plotted as well. And this is really just to highlight how degenerate the Fisher information matrix is in the classical model. Most of the eigenvalues are very, very close to zero or equal to zero. But on the quantum neural network, this is not so, right? So this was what actually got me very excited about the work, because I think for the first time we found something that that differentiated a quantum model to a classical one in a meaningful way. And we then scale these models up, right? So I should probably also say the input size in the quantum neural network also corresponds to the number of qubits in the model. So we started like increasing this, and this trend in the spectrum really persists. So this kind of more evenly spread distribution of eigenvalues in the quantum neural network, it sticks around, right? And also the if you look at the x-axis, this more or less stays constant, right? So the condition number is stable. Whereas on the classical side, you suddenly get these like large eigenvalues and huge degeneracy, like most of them are equal to zero. And this is actually really consistent with what is found in classical literature. So the Fisher information matrix is known to be highly degenerate in classical neural networks. And the reason for that is actually due to the nonlinearities injected through the activation functions. It's really quite cool. I think Jan LeCun was actually like the pioneer behind finding this out for the Hessian, and the Fisher information, for those who are interested, are like closely related, which I'll talk about a little bit later. So what's interesting is that, okay, we find something on the classical side that's quite consistent with literature, but then what does this mean on the quantum side, right? So these this distribution here with most of the eigenvalues around zero and these large spikes is actually known to slow down optimization of machine learning models, of neural networks. And the reason is because all these eigenvalues that are around zero, you can think of it as your model landscape. So you want to optimize your model landscape, right? So you want to find generally like the global minima of some cost function. And when you have lots of eigenvalues that are equal to zero, then this corresponds to a very, very flat landscape. So it's very difficult to optimize this model. So this is exciting, right? Because this is not what we have in the quantum model. But then we also wanted to see like what happens if we change our quantum model, right? So we picked a very specific architecture, and the reason we did that is because we thought that it was a good model. So there was actually I have probably also said earlier, when we chose the architecture for the quantum neural network, we chose it because we believed, because it's motivated in the paper that I referenced, to be a difficult circuit to simulate classically. So then we thought, what about like these bad quantum models, right? Well, these models where we have data encoding strategies that are easy to simulate classically. So in particular, we introduced another model, which we call the easy quantum model. And the easy quantum model has a very straightforward feature map. It has a very straightforward data encoding strategy. So if you have a data point, let's say it's this vector here with 4 entries, so 4 features, the easy quantum model will take these 4 features and encode it with some RZ rotations, and the angle of the rotations is equal to the feature values, right? So you need 4 qubits to encode this data point, for example. There should also be Hadamard gates here, which I left out. And if we compare this to the other encoding strategy of the quantum neural network, right, so the harder quantum model, we do a similar thing where we encode the feature values in these RZ rotations, but then we also have entanglement between qubits, and we also encode something called the higher orders of the data. So we encode the products of the feature values as well. So not just the individual feature values, but also some products of every pair of them. So this is the difference. So we would expect the easy quantum model to perhaps be less expressive, right, than the quantum neural network, which we see has very high capacity. So if we go back then and calculate the effective dimension, this is exactly aligned to our intuition, where we see this drop-off in capacity, where this easy quantum model has less expressibility or a lower effective dimension than this quantum neural network, but still significantly higher than the classical neural network, which is still quite interesting. So I guess then the next step, right, is to go back. This is not so important, but basically we just confirmed the results using a different measure called the Fisher-Rao norm. So this is just to verify that the effective dimension is actually giving us something that we see that's aligned to another measure of power. So if we go back then to the spectra, right? So the Fisher information spectra, I think this is really like where the interesting things are happening. We also plotted the spectra for the easy quantum model. And what's interesting now is that like for smaller input size, we can see more or less like an even-ish distribution similar to the quantum neural network. But as we increase the number of qubits in the model, then the spectrum starts to become more degenerate. And so now I don't think it's very straightforward to immediately conclude that that the landscape starts to flatten and we have bad optimization properties and all these kind of stuff. So really like the next step we wanted to investigate was how can we tie the effective dimension of a model to trainability? And it turns out that we can exploit already very, very nice literature from the classical side. So the Fisher information and the Hessian matrix, something I mentioned earlier, are very closely related quantities. So for those of you who don't know, so the Hessian matrix is basically in machine learning, you have cost functions associated with your model, which you want to minimize. And so the Hessian is the second derivative of your cost function with respect to the parameters. But intuitively, it gives you insight into the curvature of your loss landscape, the landscape that you want to find the minimum of. So it tells you how curvy this landscape is, or how sensitive it is also to parameters, right? And so under certain assumptions, like certain loss function assumptions, the Fisher information and the Hessian are very, very closely related. In fact, they coincide in some situations. And so because of this relationship, we can actually leverage all the beautiful literature there is classically about the Hessian and what it says about loss landscapes and you know, like generalization properties and so on. And so this is quite cool. And this is like something we can say concretely about classical models, which we know, right? So I put earlier that like these degenerate Fisher information matrices correspond to like bad optimization qualities. And this is the reason why, because we can connect it to the Hessian and make these statements from literature that exists. And on the quantum side of things, there is actually also some research on the Hessian and its effect in quantum models. So again, just for those who aren't aware, there is a phenomenon that's inherently quantum called barren plateaus. And the problem of barren plateaus occurs when you are trying to train your quantum model, but your gradients vanish. And so what this paper shows is that if your model is in a barren plateau where your gradients vanish and the landscape becomes really, really flat, then the entries of your Hessian also go to zero, so that the entries of your Hessian also vanish. Yes? Is there a question? Okay, sorry, I thought I heard somebody say something. Okay, so the entries of your Hessian will vanish if your model is in a barren plateau, and this is really bad, right? And so we also trivially kind of extend this idea to the Fisher information. And we wanted to understand, well, if your model is in a barren plateau with these vanishing gradients, this flat landscape, will the entries of the Fisher also disappear? And it turns out that this is also the case. So if we go back to the spectra of the models where we have like this degeneracy increasing, so this increases actually the likelihood of your model being in this barren plateau, meaning you can't train it. So this is really bad. And we know on the classical side that this spectrum is bad. Then when we train these models, we should expect this one to train the best and have the most desirable optimization properties. So the last step that we wanted to show was really to confirm this, right? Confirm this notion. And so we did a very small experiment and we trained these models. So what you're looking at here is each model trained on a very simple data set, the iris data set, a subset of it. And the green line is the quantum neural network, which trains to the lowest loss value for the fixed number of iterations. So it trains to the lowest loss the fastest. And the classical neural network actually has like the highest spread, which is quite interesting. And here, kind of somewhere in between, is this easy quantum model. And what we also further did was we actually demonstrated that we can train. Okay, is somebody talking? Mark, can you please mute them?
Yeah, I'm going to mute them clearly.
Okay. Thanks. Okay, so yeah, so we managed to demonstrate this experiment on real quantum hardware, which I think is really quite nice because everybody thinks that these things are very theoretical, but we actually show that we can train this model, and it actually trains better than the simulations, which is quite interesting. So we used IBM's Montreal device using 27 qubits, and well, sorry, not using 27 qubits. It's a 27 qubit device. We only used, I think, 4 qubits for this training, and it trains very nicely, very quickly, very fast. Okay, so what I have showed you so far is that well-conditioned quantum neural networks. When I say well-conditioned, I mean these ones with like this interesting feature map. They have higher effective dimensions, and they also have a more even Fisher information spectrum. And this is really desirable from an optimization point of view, and these models can also train faster. Okay, so while this is all very interesting, it also opens tons and tons of doors for like further research questions, further, I don't know, further things to just like wonder about, explore, and think about. So for me, particularly, I think what is probably the most obvious or pressing question is really like to investigate more deeply why this particular quantum circuit, this one with this hard feature map, this interesting feature map, why does it exhibit all these desirable properties, right? It's where it's easy to train, it's fast to train, it has high expressibility, and what does this actually mean? Like on a fundamental level, why this model and why is it performing so well? And if we can answer this, if we can figure out theoretically or I'd say analytically why this particular model, then we can maybe start to design models such that we can choose, I don't know, maybe certain data encoding strategies, certain feature maps, such that we can construct or understand the loss landscapes of our model. So we can construct good landscapes that are easy to optimize, landscapes that avoid barren plateaus and these problems that are inherently quantum. And then also like the effective dimension on its own is totally interesting, right? Like there in machine learning, there is this whole field of capacity control where you try to use these capacity measures like the effective dimension to generalize well, to get your models to perform well on unseen data, but you need to avoid overfitting, right? So where do you increase the capacity in your model such that you avoid overfitting? Because infinite capacity is not necessarily always a good thing. So this is also something that could be explored. And then I mentioned this, I think, more than once throughout the presentation, but if we can eventually make a statement about this, that quantum models can actually generalize better than classical models, meaning they can perform better on new data, on new tasks, then I think we are really, really in the money or in the gold here. Like we found gold with quantum machine learning. And then I think people will really have to take at least theoretical quantum machine learning quite seriously if we can eventually say something here, which would be really, really fascinating. Okay, so I think this is my last slide. I want to just go back to this question of are quantum neural networks relevant? Unfortunately, I don't know, right? So I haven't answered this question as Mark hoped I would, but hopefully what I've showed you manages to convince that they're not so irrelevant, right? So there actually are perhaps really interesting quantities, and we are just so early in the game that there's just so much left to explore, to understand, to verify, and it's really an interesting space to be in as a researcher. And I think that there's a lot of potential here for these quantum neural networks, for these quantum models to offer us, maybe not, all these speed ups and these exponential speed ups that everybody's focused on, but maybe something different in terms of expressivity, in terms of computation, and so on. So this is just something I wanted to leave you with. And yes, that is my last slide. So please feel free to contact me, and yeah, and if you have any questions, just ask away.
Thank you, Amira. That was fantastic. There were many questions. I think some of them you might have answered during the presentation. They were asked early on, but let me read them anyway. How does effective dimension behave as a function of stochastic noise in gates?
Yeah, good question. So we actually simulated the effective dimension using different noise models, and it turns out that it's actually quite robust, right? Because it's like an average over models, and it seems to be quite robust to noise. So we just simulated with like basic noise models using Qiskit, and the noisy simulations very closely match the noise-free simulation. So this was quite cool, quite interesting. Hello.
Did you?
Sorry. Okay.
Yeah. Did you use Keras Tuner or ENAS for the classical neural network?
No. So we used PyTorch and just use a standard PyTorch framework. So yeah.
How did you introduce noise? Did you flip the labels?
That is a very good question, and that is totally correct. So something, I mean, this person is, okay, I can't go back to the slides too far in the beginning, but I think this relates back to the experiment where I showed that the effective dimension can capture this generalization behavior. And the plot actually goes up to 50% randomization. And that is because we introduce noise by flipping the labels. That's correct. But there are other ways to introduce noise. And depending on how you do that, then you should actually go up to 100% randomization in this experiment. So that's a very good question. And thank you for asking that.
Yeah. So Ben Cordier says, this is a result I've been hoping for over 2 years now. Really interesting, amazing work. What are the loss function assumptions? When do the Fisher matrix and Hessian coincide?
Yeah, so this, thank you for the very nice comment. And I think there are two cases where the connection is quite concrete. So the first is in the case of mean square error, then you can decompose the Hessian into essentially two matrices. And the first one directly corresponds to the Fisher information. The other case is when you assume that your loss function is the log likelihood of your model. So you assume a log loss function. And in this case, then if you look at the definition of the Fisher information and the Hessian, they're identical with a difference in sign. So I think one is just the negative of the other. And these are very, sorry, these are just very, I just want to add that they're very general assumptions, right? So everybody kind of uses cross entropy loss functions and mean square error all the time. So you don't really lose anything in making these assumptions.
Can Hessians be used in place of gradients for descent since it is a smoother landscape?
Yeah, so second order optimization is something that has been shown to work very well, right? But the problem, of course, is when you scale these models up to higher dimensions, then calculating the Hessian and the Fisher even is very expensive computationally. So while they can be used, they're often not used in practice, especially in deep learning, because it's just really, really difficult to calculate them. But I think if one has the option, the second order methods converge a lot faster. And why? Because they understand the curvature of the landscape, right? So they can use this knowledge to find the global minima a lot faster.
Do you have any comments on how these results compare against the article Power of Data in Quantum Machine Learning? And they give a link where a higher dimension of the parameter Hilbert space is actually bad for the prediction error.
Yeah. So yeah, this is a very nice paper that came out by Google, I think maybe a week after we published our results. I think they're very, very unrelated, right? So what we do is we take a classical measure, essentially, or just a measure that can quantify the expressibility of any model, of any statistical model. So as long as you have a statistical model with a probabilistic output, you can use the effective dimension and you can make statements about it. And so the theoretical proofs of our results really are centered around the effective dimension. And then the numerical results really just like calculated for a specific model, right? For a specific quantum model. So we don't make any theoretical statements about the class of quantum models. We don't do this. And this is very much the next thing that I would like to do. So whereas on the power of data encoding, I forget the title, but the Google paper, they they try to bound things like for classes of quantum models. So this is really like more theoretical what they do. And I think the two are quite unrelated, actually.
What are your thoughts as to why running on an actual device performed better than the model? Does noise help in this case?
I was hoping somebody would ask this. So so one thing I didn't mention about this actual implementation here is we change the entanglement structure. So why do we do that? Well, because we initially believed that more entanglement was better, right? So this introducing more correlations would be better for the model. So this green line here has more C0 gates in it. But then to actually implement it on near-term hardware, we had to reduce the number of C0 gates to make it actually run in a timeline that was doable for us. So we took out some of the C0 gates, and in doing so, I believe that this is actually the reason why the model trains better. And there's a paper that came out not so long ago called Entanglement-Induced Barren Plateaus, where they discuss like the role of entanglement and how this actually affects your model, and introducing more entanglement does not always mean better performance. And so maybe this is the reason, but this will have to be further investigated.
Was the training done in batches on the quantum computer?
No, it wasn't. It was full batch. I think I mentioned, yeah, full batch.
For very large data sets, is there a theoretical improvement in efficiency, like power consumption, for quantum neural networks in light of recent events at Google?
Yeah, I'm not sure. I think maybe read that paper where the link is in and check it out. I think this is a very broad question, and I think there might be statements around very specific problems or instances that this might hold true. But I don't know. Yeah.
I think Togan wants to ask a question in voice.
Okay,
Togan,
cool.
would you like to?
Yeah, hello, thank you. Can you hear me?
Yes.
Yeah, great. Thank you very much for the presentation. So my question, maybe it's a little bit basic, but with regards to optimization algorithms like the gradient descent, they have been like using the quantum neural gradient, which is used to sort of optimize the variation quantum circuits. Is it possible to use such models in classical machine learning models? Like, for example, if I have a linear regression model, can I just choose to use like a quantum library when I can just take advantage of the quantum neural gradient, like a hybrid model, classical quantum hybrid model?
Yes, so you can definitely, yes, okay, so you can definitely do this. You can definitely create a hybrid model. And I think there's actually even a nice chapter in the open source textbook, the Qiskit textbook, so Qiskit, Qiskit, on where they build a hybrid quantum classical neural network and optimize it using like some PyTorch optimizers. And then you can, of course, also use like quantum natural gradient descent and all these like quantum optimizers as well. I think this will also be fine and this will also work. But something that was interesting when you asked your question that came up in my mind was I thought you were actually asking, won't this model still be trainable using quantum natural gradient descent or just natural gradient descent, right? So this idea of using the Fisher information to find the minimum. And something I just want to point out that optimization might not actually be slow if one uses a different optimizer here. So if one uses natural gradient descent, for example. But the problem with this is when you scale things up, the Fisher information is not always calculable. So that's something I just want to mention. Sorry, it's irrelevant to the question, but something I thought about.
Thank you very much.
Cool. Thanks for your question.
So this is a question which is actually general, not specific to your talk. Moore's law seems to have plateaued for binary chips, whereas RISC chips appear to extend Moore's law into the foreseeable future. At what point do you see quantum computers supplanting them?
Oh my gosh. So firstly, I must disclaim, so I think I know who asked that question, but I must also disclaim that I am not a hardware person at all. So I'm totally not qualified to make this answer or this statement. So I guess I can say confidently that I have no idea.
Fair enough.
Cool.
What do you think about the Chinese quantum computer that claims to be 1,000 times more powerful than Google's?
Yeah, I don't know, right? Very interesting. What I love so much is that like all these different all these different places, all these different companies, all these different people are trying new architectures, new ideas, new methods for improving their devices. And so like the progress on the hardware side of things is really fascinating. I mean, I must admit, I'm not a hardware person, so I don't fully understand. But as a theorist, it's exciting because it means that like our algorithms can perhaps be soon implemented on these devices. So yeah, I'm very excited about this.
So this isn't directly related, but a recent result by Siliberto and others this year indicated that quantum machine learning algorithms can't achieve polylogarithmic sample complexity relative to the input when accuracy is taken into account. Do you see any connections between your result and theirs?
So no, so something I really want to look into afterwards, so know about the connection. Something I also really want to look into is the effective sample complexity using the effective dimension. And then I think maybe there could be some connection here. So this is an interesting question, and thanks for bringing it up. So yeah, this is something I really want to look into.
So so I think that's it, unless anyone has any further questions. Thank you so much. That was fantastic.
Sure.
And thank you especially for answering all of those questions.
Thank you for having me. I really enjoyed it. Thanks a lot, everyone, for attending. And I know it's like daytime for you, but nighttime for me. So thanks a lot, everyone.
Yep. Thank you, Amira. Thank you, everyone.
Ciao.
Bye.